start the recording. Sorry, the part of the introduction is lost. Now, so we shall record it if you don't mind.
Excellent. Perfect.
Okay. Thank you. Sorry.
No worries.
Okay.
So we have capital N molecular species. The state of the system is described by a vector, which takes discrete values. And as mentioned previously, the eth component corresponds to the abundance of species Si. The species interact with a finite number, capital M, of chemical reactions. And every time the kth reaction fires, the state of the system is displaced by a stoichiometry vector. We also introduce a propensity function whose components are labeled lambda k. And these propensity functions depend on two things: the state of the system, x, and a parameter vector, theta, who has d components. And with these ingredients, namely the stoichiometry vectors zeta k and the propensities lambda k, we can express the continuous of Markov chain x theta t. Now, it is just important if you were to look into the details of the proofs of the manuscripts which the presentation corresponds to be aware of the different ways the reaction dynamics can be specified. So the first one, maybe the most usual one for continuous star Markov chains, which I will call CTMC from now on, is through the generator, which you can see as a possibly B infinite matrix, which is given by this. I will not spend a lot of time on this, as it's not the description which I'm commonly using, but it's maybe useful for people who are more familiar with other types of CTMCs. So this generator Q can be seen also as an operator on probability measures. It is used to express the chemical Marceau equation. And in the general stochastic process literature, Q is also known as the transition or jump rate matrix, and the CME is often known as the Fokker-Planck equation. Now, second way to specify the CTMC is through the generator A theta, which can be seen as an operator on bounded real-valued functions f, with the action of A theta on f being described by this right-hand side. And here note that the finite difference, which is in the parentheses, will be like simplified to this notation: delta zeta k f. Now, A theta can also be seen as the possibly B infinite matrix, and it's the adjoint of Q. It is used to express the Kolmogorov equation, so Kolmogorov forward and backward, and the Martingale problem for the process x theta. Now, a third and last way to specify the reaction dynamics: you introduce a collection of independent unit rate Poisson processes to define a counting process RK, through this expression. So this should be read as the Poisson process indexed by k at time, with this expression into the parenthesis. Now, this counting process associated to reaction k increases by 1 every time the kth reaction fires. With this at hand, we can specify the dynamics of the CTMC through a stochastic evolution equation, which look like that. So here we are summing over the reactions. You recognize the stoichiometry vector zeta k and the reaction counting process RK at time t, which we just introduced above. And in the literature, equation 4 and 5 are often referred to as the random time change representation of x theta. Now, just to rehearse what we just introduced, so the takeaways from the introduction: reaction networks naturally arise as a descriptor across the life sciences. Takeaway 2, stochastic models are often required in molecular biology. Takeaway 3, stochastic reaction networks are continuous time Markov chains. And takeaway 4, the reaction dynamics can be specified in multiple equivalent ways. Now, closer to the topic of today, I will give you a brief introduction to parameter sensitivity analysis. So, I mean, the definition is quite straightforward. Parameter sensitivities are simply the derivatives of expected network outputs. Just to make things precise, we consider an output function f and a terminal time t. And let's say we are interested in predicting the expected network output, which we define through as psi. And through so it's just the expectation of the output of f. The value of the parameter is frequently uncertain, and so it's of interest to quantify to which degree the prediction made about the systems are going to be affected by a change in parameters. So a natural measure of this degree is through the derivatives. And so we, for example, introduce the first order parameter sensitivities, like simply as a derivative of the expected network output. So now I'll focus briefly on first order sensitivity, and I'll highlight that the sensitivities are the basis for both theoretical and numerical approaches. So the motivation one is just what I said in the previous slide. So if you are interested in quantifying the robustness of the prediction to the value of the parameter vector, or to the presence, absence of specific reactions, you might be interested in the value of the sensitivities. A second motivation is anywhere where you need a gradient of the expectation, for example, in inference procedures, you will need the sensitivities. And the third motivation, which refers to the theoretical approaches which I'm mentioning in the title, is that if you have representation of the sensitivities, especially in the stochastic modeling framework, you can investigate system properties like robust perfect adaptation. I'm not going to cover this today, but I refer you to these two papers from our group. And in the first paper 9, especially to the supplementary material, where the connection between sensitivity analysis and the concept of robust perfect adaptation is highlighted. Now I'm going to mostly focus on numerical methods to estimate sensitivities, which fall broadly in 3 categories. So if you open any stochastic simulation book, like the one by Asperson and Glynn, you will find that, so this is just an excerpt from the table of content, you will find finite difference methods, infinitesimal perturbation analysis methods, and the likelihood ratio method. So these are the 3 types of sensitivity methods. And I'm not going to cover them any further for first order sensitivity, but I'm going to introduce them for the second order. And now I'm highlighting that, so what I showed here was the textbook knowledge. And now there has been this generator gradient estimator, which has emerged as the 4th class of method. So in a 2024 paper, the 3 authors, Wang, Blanchet, and Glynn, introduced these generator gradient estimators for jump diffusion stochastic differential equations. And so we've put a small note on arXiv so far to highlight the connection between an estimator which was developed in the group earlier, so this exact integral path algorithm. And it's quite striking to see that finite difference between become derivatives. So you have all the transformation which you would expect if you go from the framework of SDEs to CTMCs, but essentially the formula which you get is exactly the same. In this note, we also demonstrate that the generator gradient estimator is an advanced state method. And why is this interesting? Is that so advanced state methods don't scale with the number of parameters. And this is of interest if you have a large number of parameters, as you have for deep neural networks, especially in the context of neural SDEs. And the EIPA, so the algorithm in the context of TTMTs, also doesn't scale on the number of parameters, but it scales with the number of reactions. So takeaways from the introduction on parameter sensitivity analysis. First takeaway is that parameter sensitivities are defined as the derivatives of expected network outputs. Takeaway 2 is that sensitivities are the basis for theoretical and numerical approaches. Third takeaway, numerical methods to estimate sensitivities broadly fall into 3 categories. And last takeaway, the generator gradient estimator has emerged as the 4th class of methods. So we've completed this introduction in so the first phase of the talk. And now we'll jump for the second phase, which is closer to the title and to the manuscripts which I will be presenting. So to give you the outline, first I will more specifically explain the sensitivity methods for second-order parameter sensitivities. Then I will present you an integral formula for second-order parameter sensitivities. In the third part, I will explain how to construct an unbiased estimator of second-order sensitivities from the integral formula. Then I will exemplify the algorithm and the unbiased estimator introduced in the previous part through numerical examples. And then I'm going to give you a brief summary and outlook. So, estimation of second-order parameter sensitivities. Why is this of interest? Why is it not enough to just look at the first-order sensitivities? Well, let us first introduce some notations again. So here I've introduced the second-order parameter sensitivities, which are just the second-order derivative of this expected output. And just as a reminder, so I and j are going to be the indices of the parameters. X is the initial state, f is the output function, and t is the time at which you're interested in which you're interested in. So you can first look at this formula and give the usual interpretation for second-order derivatives. It's just the curvature of the response surface, which is information on top of just the gradient. Then the second motivation is that usually when you run your parameter inference procedure, you end up with a gradient which is close to 0 and ideally 0. But then you might be interested in the parameter uncertainty which you have in the estimated parameters, and that's precisely the information which is carried by the second-order derivatives, so through this curvature of the loss landscape. Now, third motivation is that in a growing number of experimental setups, the response of your chemical reaction networks can be influenced by cues like chemicals or light. And depending on the cues with which you interact with your system, you will have more or less identifiable measurements. And so through the second-order sensitivities, you can select the most informative inputs as part of a procedure which is commonly referred to as experimental design. And fourth and last motivation is that the second-order derivatives are used in efficient optimization routines like the Newton-Raphson algorithm. And then these optimization algorithms can themselves be used for system identification or the design of control mechanisms. And I've listed a couple of papers to introduce the different points which I've made on this slide. So previously, for first-order sensitivities, I mentioned this likelihood ratio method. In the field of chemical reaction networks, it is actually usually called the Girsanov transform method. And this provides an unbiased estimator of second-order sensitivities. So this is the formula, which I'm not going to spend too much time into each part of the formula, but the structure is important. So it's the f is the output function. So it's f as it's the function of the state at the terminal time times some terms where you have integral against the reaction counting processes and against time. And maybe unsurprisingly, you have first-order derivatives of the propensities and first-order derivatives. As I mentioned, the Gieselmann transform is also known as the likelihood ratio method in numerical analysis in general, and as the reinforced algorithm, mostly in the reinforcement learning field. So I'm just going to list a few characteristics. The first one is that the existence or the applicability of the Gieselmann transform method, which I will abbreviate as GT, depends on the existence of, first, a stochastic exponential, and second, the validity of an interchange of derivation and integration. So there have been conditions which have been proposed for first-order derivatives, but they can be challenging to verify, and they have not yet been derived for second-order sensitivities. Now, to explain the second characteristic, I just printed again the expression from the previous slide. And I mean, it is quite easy to see that if some of the propensities are proportional to theta I or theta j, and the parameter being evaluated as 0, then the formula itself is just not defined. And this precludes the investigation of the sensitivity of an output to the presence-absence of a reaction. I mean, among other, in the important case of mass action kinetics. So this is a major blocking point. And the presence-absence is especially interesting if you, for example, want to test how much your prediction is going to be affected by removing an uncertain reaction. Now, a third characteristic is that it has been observed that the GT method suffers from a large variance, not only for the case of the SRN, so this type of models, but also for a range of other stochastic models. And I've given you the reference 25, where they do this in a completely different context, for example, in machine learning. Now, the second type of method, which I mentioned for first-order derivatives, is finite difference methods. So for second-order sensitivities, you need to introduce like 4 parameters. Here, EI and EJ corresponds to the vectors which are all 0 with only a 1 in position I or j. So the basis vector of Rn. And so here you have 3 perturbed parameter, and the 4th one corresponding to the nominal value of the parameter you are interested in. And then you can define these finite difference methods just by approximating the second-order derivatives in the usual way. And so you usually introduce 4 processes, where the process indexed by L has generator A theta L. So to this process 1, you associate the parameter theta 1, which is defined like that. I mean, this is we usually write this expression just for convenience, notational convenience. But so this equation you usually replace by its centered equivalent, which has a bias of order epsilon squared. But then, I mean, the performance of your estimator is going to depend not only on its bias, but also on its variance. And in order to reduce the variance of estimators which are based on this formula, you try to couple the processes to reduce the variance. And among the couplings which have been suggested in the literature, we are highlighting the split coupling, which has variance of order epsilon minus 3, which has been introduced by David Anderson and his student Elisabeth Wolf. So the first characteristic is just going, I mean, if you consider the last 2 points, is that if you want to reduce the bias, you will dramatically increase the variance. And so this was also the case for if you consider first order, but it's actually much more pronounced for second order sensitivity than for the first order, where you also had a bias of epsilon squared, but the variance was only growing at epsilon minus 1. And for second order, what I mentioned is of order epsilon minus 3. just to illustrate it graphically, this is bias variance trade-off plots. So this is for the first order sensitivity, and here it's for second order. And I've printed the variance for a range of biases, which correspond to a range of epsilon. And as you see, if you reduce the size of epsilon, of course, your bias diminishes, but then your variances increases. So this is the case for the first order and second order. So this numerical example is just an illustration of the orders which I've displayed earlier. But what is important to see is the magnitude of the variance here. For the first order, in both cases, we are considering the same parameters. So here it's the first order derivative with respect to this parameter, and then here it's a second order derivative with respect to the same parameter. Here the variance is order 10, and here it's order 10 to the power 3, for exactly the same epsilon. And here, so it just illustrates that things are this bias variance trade-off is going to be much more detrimental for second order method than for first order method in the case of finite difference methods. And now, second characteristic is that if you look at the Gieselnov transform method, with one sample, you can generate an estimation of the whole Hessian at once. But if you look at the finite difference methods, you need to create all these perturbed parameters, which I showed earlier. So these parameters. And I mean, the numbers themselves are not that important, but the takeaway is that for each derivative you're interested in, you need to create all these perturbed parameters, which is going to be more and more costly as the number of parameters you're considering increases. So this was the tailored introduction for second order sensitivity. And now we move to the content which is presented in a manuscript which is already on the archive. And we are starting with an integral formula for second order parameter sensitivity. So I'm just putting the notations again for expected output, first order sensitivity, second order sensitivity, which are just the same as previously. And what we established in this manuscript is that you can actually represent your sensitivity, second order sensitivity, as the expectation of some quantity, which is displayed here. Like for the Gieselnov transform method, you have second order derivatives of the propensities and first order derivatives of the propensities. And then you have these finite differences of the expected output and of the sensitivity, where you have the finite difference of the expected output in front of the second order derivative, and you have cross terms of the finite difference of the sensitivity for the first order derivative of the propensities. So I'm not going to present you the whole proof as it's quite long, but I'm still going to give you the gist of it. And namely, I mean, the core idea is that we actually use the speed coupling processes, but not, I mean, just for the numerical method, but we use it as an analytical tool. And this speed coupling has already been used in other contexts in the literature. For example, related to proof of the tau leap. So it's just a useful analytical tool to use beyond sensitivity methods. So here I mentioned that the proof builds on ideas introduced in these three papers, which are, I mean, these are actually in the field of sensitivity analysis. So how do we proceed? So we introduce four coupled processes from the paper of so Elisabeth Wolf and David Anderson, which I mentioned earlier. And through these four coupled processes, we can just define the second order finite difference, which we know in the limit will go to the second order sensitivity. And then we have a path-by-path approach where we first define a partition of the sample space based on the split time between the processes. So the important thing, I mean, the key idea here is that your processes are going to have the same value for some time, and at some point, one of the four processes is going to decouple. And by this observation, we can look into which reaction counting process caused the split. And then you have some quantities which you can consider in turn and take the limit. So this is the first step, and the second step, it's essentially just reshuffling the term and simplifying them. So, so we've obtained this second order sensitivity formula, but which is of interest in its own right. But we wanted in this project to construct an unbiased estimator of second order sensitivity to address some of the shortcomings of the Girsanov transform method and of the finite difference methods. So I'm going to explain you, for example, how to do it. So in equation 12, which was the theorem which I displayed, you have three terms, and I'm going to look first at the first term. And this is broadly inspired from an approach which was developed for first order sensitivity methods. We will use this additional notation where instead of just indexing the process by time, we also index it by x, the initial state. So here, this should be read as it's the process x theta considered at time t when it started at from state x at time 0. So we introduce now what we will call first order auxiliary processes. So here I'm going to go step by step. So we have pairs of first order auxiliary processes. The index p corresponds to the jump time of the process, which here is sigma p. K is used to refer to the reaction, which you see here through the stoichiometry vector zeta k. And 1 and 2 is going to refer to the fact of whether you have this stoichiometry vector added as the initial condition or not. So just to state it again, so if you consider this process x theta pk2, it means that you started from this state perturbed by this stoichiometry vector at time 0, and you then consider it at time t. So with these tools, and so the first order auxiliary process, which I just print here again for convenience, we can work on the first term of the theorem which I've displayed earlier, namely the one which has the second order derivative of the propensities times the finite difference of the expected output. And then we need two observations: the fact that trajectories of the main process x are constant between jump times, and the Tauer property of conditional expectations to move from this expression to this expression, which doesn't require, and the important observation here is that this term doesn't require knowledge of the expected output. So you can just evaluate this purely based on simulations. Now, with very similar ideas, we can introduce second order auxiliary processes exactly in the same way as the first order auxiliary processes. And with all these auxiliary processes, we can generate one sample of the whole Hessian for multiple output functions from a single trajectory of the main process, exactly in the same way as it was the case for the GT method, so the Girsanov transform, but with the hope, of course, of having a reduced variance, which we are going to cover in the subsequent part. Second observation, which is important at this point, is that the trajectories which you are generating, you can still use them to estimate other quantities like average output or the Jacobian. from exactly the same trajectory. So it's so you have a hierarchy where if you're interested in second order sensitivities, you don't need to do some specific trajectories, but you can have the whole information. So zeroth order derivative, first order derivative, and second order derivative in one go. Now, so I'm going to introduce two improvements on this like core idea to reduce the variance of the estimator. The first idea is that we are going to again use the split coupling, this time not for analytical consideration, but to reduce the variance of the estimator. So here it's useful to see that we take difference between processes, and the idea is that you couple these processes to reduce the variance of the difference. Then second improvement is that in the previous expressions, every time there's a jump, you need to generate these auxiliary processes. So we introduce Bernoulli random variable, whose rate depends on the derivative of the propensities, to control the number of processes which are being generated. So just as an illustration, here you can put a Bernoulli random variable to decide whether at jump time sigma p, you're going to generate auxiliary processes to compute this integral. So this was with words, and I'm going to quickly show you graphically how that looks like. So you have this main process, and let's say you have two reactions. Every time there's a jump, you have to consider this balanced binary tree. So one related to reaction K and the other for reaction K1, sorry, and then the second for reaction K equal 2. You will have first order processes, one which corresponds to the unperturbed parameter, to the unperturbed reaction, sorry, and then to the perturbed one. And then these first order processes will also generate second order processes, again, each time where you have the unperturbed initial state and then the perturbed initial state. So this is the full structure. And the number of leaves here is 4 times m squared, where m is the number of reactions. So this is like the core algorithm which I mentioned earlier, but with the modification, namely the coupling and the Bernoulli random variable, it will look like that. So you run your main process, then you have to consider perturbations of the initial state through reaction K equal 1 and reaction K equal 2. So you draw your Bernoulli random variable. If it equals 1, you generate the first order processes, the unperturbed one and the perturbed one. And then to decide whether you generate the second order processes, you again draw random Bernoulli random variables. And depending on the outcome, you generate or not second order processes. So you move from having to generate the whole balanced binary tree to just generating some of the differences of the second order processes and the first order processes. I'm now going to show you some numerical examples. We are going to do the comparison with the Gizanov transform method because it's the only unbiased estimator which we can compare with. We know that, I mean, they are unbiased, so they will converge to the exact value, but we can expect that they will have different variances or mean squared errors for a finite number of samples. The second observation, which is important here, is that the cost per sample is going to likely be different between the both methods. So just the rule of thumb is that the Gizanov transform method has just the cost of stochastic simulation. And with the algorithm which we introduced, so the double BPA, you are going to generate all these auxiliary paths, which will have additional costs. But the hope, again, is that through this additional cost per sample, you're going to have a variance which is going to be reduced. And because you have to take into account the variance and the cost per sample, we introduce this MSE T computational, which is the variance of one sample from the DBPA or Gazanov transform divided by n bar T comp, which is just the average number of samples generated with a computational budget T comp. Now we introduce two quantities, M naught, which is T comp divided by this n bar, and calligraphic M, which is again calligraphic M naught times sigma squared, which is just the variance adjusted cut per sample. And so we can rewrite the expression 15 into this. And here you see that in the end, this expression for the MSE only depends on this quantity calligraphic M, which you need to estimate. And once you have it, it fully characterizes the relative performance of the two unbiased methods, so namely the Gazanov transform method and the DBPM. We have run several examples in the manuscript, so you could look at the main material and the supplementary material. And I'm going to focus on one example today, which is the gene expression network under the control of an antithetic integral controller, which is of interest to our group in particular, but also by a larger community of people who want to also use it for engineering purposes. So here I'm going to, this is just the reaction which describe just gene expression under antithetic control. And these are the propensities corresponding to it. So I'm not going to spend a lot of time on this to it, but I refer you to this two manuscript for further details on the application of the antithetic integral controller. And I'm going to directly move to numerical result. So with two plots, which I'm going to explain you shortly. So this is on the left, you have a plot of the estimate of the second order sensitivity by the two methods, so the DBPA and the Gazanov transform. So the DBPA is in blue and Gazanov transform is in yellow. And we've computed the estimate for a range of times. And this is when you consider the output as being the square of the abundance of the second species. So here you can already see that the error bars are much larger for the Gazanov transform than for the DBPA, although we used 10,000 samples of DBPA and 500,000 Gazanov transform simulations. But as I mentioned, these two methods have different costs. So what is important is to look at this calligraphic M. And here you see that with time, the cost of the Gazanov transform, grows, increases significantly. And the one of the DBPA stays relatively constant. And so this difference is 2 orders of magnitude. And I'll refer you to the manuscript for more illustration of this gap. And so the takeaway is that despite this increased cost per sample of the DBPA, you can increase variance reduction, which translate in a lower, improved performance, even if you take into account the computational time performance. Now I'm going to move to the summary and outlook. So summary, 4 points. The first one from part 2 is that we've provided condition on the existence of second order sensitivities. So this I did not cover in the talk, but I refer you to the manuscript. Related again to the second part with the integral formula is that we've actually provided a new integral representation for the second order derivatives. Related to the part 3 on the construction of the estimator, we've introduced the double BPA. as an algorithm to generate unbiased sample of the Hessian of an average output, which take the form of expected output of some function of the state at some time. And then related to the part 4 is that we have illustrated on a couple of numerical examples that the double PPA can provide a substantial performance improvement over the only unbiased alternative, which is the Gizanov transform method. Now, in terms of outlook, so the first thing which you might say is, well, for the WPA, you need some exact simulation algorithm. And this simulation can be computationally demanding, for example, if you have a timescale separation. So in the spirit of this paper for first-order sensitivities, you could approximate the exact simulation by Taulib algorithm and still use this new representation which we've provided as the starting point. Second outlook is that, so in this reference 39, the equivalent of the second order representation formula was used for first order sensitivities in what was called the DPCME framework. And in this paper, the expected output was first approximated using a neural network, and it was this surrogate which was used instead of the auxiliary path, which is the extra cost which the WBP has to pay when compared to the Gizanov transform. So in exactly the same spirit, we could start from this equation 12 and have a neural approximation of the expected output and its first order sensitivities to avoid the simulations of the auxiliary path altogether. Now, in terms of a third outlook, is that you may say, so now you have a representation for first order sensitivity, second order sensitivity. How does it look for alpha order parameter sensitivities, which we just defined with this multi-index? Well, by cause inspection of the way the proof is structured for first order and second order sensitivities, we know that the formula is going to have this shape, where as for the first and second order sensitivity, you sum over the reaction, and then you need to have these binomial coefficients times this integral of time, where you have derivative of the propensities and finite difference of lower order sensitivities. So we have also outlined a hierarchy in the sensitivities. And now, as the last outlook, related to stationary sensitivities. So, I mean, we will work without, we will not be precise at this point as for the previous point, but let's just assume that X is exponentially ergodic with a stationary distribution, which we write pi theta. You can define steady state first and second order derivatives in this way. And the fact that this limit actually corresponds to the stationary sensitivity, we take this for granted, although we also know conditions for its applicability. Then we use two auxiliary quantities, the f theta and g theta, which are solution of so-called Poisson equation. And I refer you to reference 43 for some more details on the Poisson equation in the context of continuous Markov chains and stochastic reaction networks. And then we obtain this formula where, so I'm again only going to exhibit the structure. So here you sum again over the reactions, and then you take an expectation against the stationary distribution. And then you have exactly the same term as the finite time second order sensitivity. So you have second order derivative of the propensities, first order derivative of the propensities, and then you have finite difference of f theta instead of the expected output. And you have finite differences of this g theta instead of the first order derivative. with F and G being solution of this Poisson equation, which I just mentioned earlier. So, so these two results are not provided in the manuscript, but so were given as future research directions. And here you see that the structure which we've highlighted for second order sensitivity holds both for higher order derivatives and for steady state sensitivities. And with that, I thank you all for your attention, and I welcome any feedback or question.
Thank you very much for the interesting talk. And so if anyone has some questions or remarks, please.
Yeah, I have a question. Hey, Quentin.
Hello, Diego.
So you showed for the biased estimator, you showed the variance depending on like epsilon to the -3, right?
Mm-hmm.
So do you have, I know you don't have like epsilon, but do you have estimation for the variance on this method?
So I do in an unpublished version for the moment, but essentially the downside of the variance estimate which I have is that it applies if you were to know the expected output and the first order sensitivity, which you don't
Okay.
know. And
Yeah.
I have numerical evidence that if you actually know this expected output and first order sensitivity, the variance of the this double BPA is extremely low.